And now let's have a look at various sources of autocorrelation. And the first source of autocorrelation is inertia. This is a major feature of most economic time series, and inertia can also be called sluggishness. The example of such economic time series is right in front of you. It can be GNP, price indexes, production, employment, and unemployment. So the sluggishness comes from the fact that those economic variables follow sometimes business, but in general cycles, meaning that the way they change does not change over time. So at some point, all those variables increase over time, and started after some point they start decreasing and then increasing and decreasing. So you see there is a pattern in their behavior, and because of this, the problem of autocorrelation may arise. From this example, you can also get the main point that autocorrelation is most common in time series data. I don't think you will ever see autocorrelation in cross-sectional data. Another source of autocorrelation has to do with the specification bias. For example, the exclusion of important variables. If you look at equation number 3, let's suppose that this is the correct equation. You see y is the function of x2, x3, x4, but for some reason, instead of estimating this equation, let's assume we estimate equation number 4, where y is just a function of x2 and x3. So as you can see, x4 is missing in this equation. And since the correct model is number 3, but instead we estimate equation number 4, we get that the error term in equation 4 is equal to the sum of the missing x variable, x4, plus the error term. So the error term in the second equation is equal to the last two missing terms of the correct equation. And since now the error term is a function of some variable, the error term will reflect some systematic pattern creating autocorrelation. Another example of specification bias is incorrect functional form. So let's once again suppose that the correct model is this one, so y is a function of x and squared x, but again, for some reason, we do not include the x squared term and calculate the following equation where y is just a function of x. So once again, since the correct equation is number 5, but we estimate equation number 6, the error term in the second equation will be equal to the missing terms. So it will be equal to be 3xi squared plus the error term. And again, since the error term is not random anymore, it is a function of some variable, in this case x squared, the error term vi will reflect a systematic pattern creating autocorrelation. Another source of autocorrelation can be related to lags. Once again, suppose the correct model is this one, so y is the function of x and it's a function of its lag, xt minus 1. And again, for some reason, instead of including this lag, we just calculate the following model where y is a function of x. And I think you already get the idea. So since the correct model is number 7, but we estimate equation number 8, we get that the error term in the second equation is equal to the missing terms from the first equation, beta 3 xt minus 1 plus ut. So once again, the error term is a function, this time of xt minus 1 variable, and because of this, a systematic pattern will arise, leading to autocorrelation. Another reason for autocorrelation can be related to the manipulation of data. So this is something that econometricians and economists sometimes tend to do. So what they do is they take raw data and they try to manipulate it. An example of such manipulation could be, for example, deriving quarterly data from monthly data by adding three monthly observations and dividing the sum by 3. And so and because of this averaging, the smoothness comes into the data and it dampens the fluctuations of the monthly data. And because of this smoothness, a systematic pattern arises in the disturbances, and this is the case of autocorrelation. So this example actually shows you that if you get monthly data, try to work with monthly data. Don't try to transform into quarterly data. The same idea applies to quarterly data. So if you've got quarterly data, try not to turn it into annual data. So work with quarterly data. Otherwise, you might get the problem of autocorrelation. Another source of autocorrelation can be related to incorrect data transformation. So let's consider the following model in the level form. So y is a function of x. This is a traditional model, which can also be written for the previous period, t minus 1. So yt minus 1 is equal to beta 1 plus beta 2, xt minus 1 plus the error term from the previous period. And now let's subtract equation 10 from equation 9. So when we do this, we get the model in the difference form. So where delta is the first difference operator, right? And delta yt is equal to the difference between yt and yt minus 1. Delta xt is equal to the difference between xt minus 1. And delta ut is equal to the difference between ut and ut minus 1. And let's express this as just vt. So, and this is the model that we get. And now, if ut from the original model, so if the error term from the original model satisfies the assumption of no autocorrelation, so it is not autocorrelated with any residuals, then what we get is that vt is autocorrelated. So this example shows us that please do not apply first differences to your data set if the error term is not autocorrelated, if it meets the assumption number 5. Because if you do that, the error term in first differences will be autocorrelated. But when we go into the remedy section, you will see that actually when the original error term is autocorrelated, so if we have assumed that ut is autocorrelated, applying first differences actually makes the error term not autocorrelated. So the opposite. Anyway, once again, so if you have the data, please don't use the first differences if the error term in your original equation is not autocorrelated, because if you apply the first differences, you will get an autocorrelated error term, and you don't want to have it. And the last source of autocorrelation, non-stationarity. I'm not going to focus on it because we will discuss it in the next lectures. So we see the time series is stationary when its characteristics, mean, variance, covariance, are time invariant. So in a sense, they do not change over time. Once again, we will discuss it in much more details in the next videos, in the next lectures. So for now, just accept it as a fact that non-stationarity can be a source of autocorrelation.